Keep talking, folks. Keep talking. We're not starting yet. I got to introduce myself to everybody first. Hi, I'm Mel Slugbate. How are you? Nice to meet you. Let me give you a brochure here. This isn't really a very glossy piece, but that should be a nice one there. Hi, how are you? I'm Mel Slugbate. What's your name?
I'm Mike.
Hi, Mike. Nice to meet you, Mike. What are you living in now? You got a 3-bedroom, 4-bedroom? What do you got?
A 1-bedroom.
A 1-bedroom? Is that legal by law? That's incredible. That must be really difficult for you. What do you do if you have company over? I guess they share the room with you, don't they? Okay, well, we'll talk about that later. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Hi. Let me give you a brochure there. Hi, I'm Mel Slugbate. Nice to meet you. Hi. You know, we got a 900 number you can call, talk to a live real estate agent, you know? And you can ask anything you want. You can say, does the basement leak? You can say, is the paint lead-based? Anything like that. I do it. It's a lot of fun. About $3.99 a minute. I don't go for those at all. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Let me give you a brochure here. All kinds of interesting deals in there. Hi, how are you? I'm Mel Slugbate. So how many bathrooms you got right now? You have 1 bathroom, right? And what happens in the holidays? You have the family over. You don't have any family over. Well, that's one solution. Hi, how are you? I'm Mel Slugbate. Let me give you this here. There's a brochure. I think you'll find some really interesting deals in there. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Hey, let me give you a brochure there. Hi, I'm Mel Slugbate. How are you? Nice to meet you there. How would you like to have unlimited free lawn ornaments? Would you like that? And no maintenance at all. We have some houses which are situated right next to cemeteries, right? And you don't have to pay us, so you get all those lawn ornaments for free. Here, how are you? I'm Mel Slugbate. Nice to meet you. Let me give you a brochure here. All kinds of good deals in here. Here we go. There's one for you there. Hi, I'm Mel Slugbate. Nice to meet you. Let me give you a brochure there. Make sure I get to meet everybody here. Hi, I'm Mel Slugbate. Nice to meet you. How are you? Hi, I'm Mel Slugbate. Let me give you a brochure. Here you go. There's one for you. Oops, I'm getting a little tangled up here. There's one for you. Hi, I'm Mel Slugbate. Nice to meet you. Let me give you a brochure there. Hi, how are you? I'm Mel Slugbate. Let me give you one of those there. Hi, how are you? I'm Mel Slugbate. How would you like to live in a place where you could just open the door and watch the sun set on a sea of condominiums all identical to yours? Enough done that? We got a special deal there. It's really nice. How are you? I'm Mel Slugbate. In fact, it's actually a retirement community for real estate agents. But because of the fact that they're not enough signing up, we're allowing other people to sign up too. It's really a special place if you've ever spent time with real estate agents. Here, can I just pass these down to you there? If I could just pass those down to you there. I mean, those. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Let me give you one of these here. There you go. Let me go. You know, I'm going to have to just pass a few of these out, I think. Okay, I don't have to meet the rest of you. Hi, how are you? I'm Mel Slugbate. Nice to meet you. I'll give you a couple of these here. Here. Make sure I get enough over there. And over here. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Hi, nice to see you again. You know, I always felt so bad about when I sold you that house, you know, and then the plumbing went bad, you know. But I hope you're happy we moved that porta potty into the backyard. Is that working for you? Good, good. Give you a couple of these here. There you go. Let me give you a couple right here. Send those back there. Get a couple over here. 1, 2. Wow. Got a great audience here today. This is great. I should make a killing. Give you a couple of those there. Great. I'll just pass those back there. Hi, nice to meet you. It's been quite a while. Oh, thank you very much. A lot of people say that. Who does my hair? You know, I do it myself. Hard to believe, isn't it? It's this special goop I have. Actually, you can borrow some later if you like. I got it up front there. Yeah. Here you go. Let me just give you those. Great. Hi, how are you? I'm Mel Slugbate. Nice to meet you. Let me give you just a couple of these here. Make sure everybody gets one of these. Don't want you to miss out on any of the opportunities. Here's some good ones right here. How's that house working out in Iowa I sold you?
Yeah, that's nice.
Is that nice? Yeah, you like that there? Yeah, we have trouble selling houses out there. 1, 2, 3. There you go. Uh-oh, I'm getting down to the bottom here. But actually, you might, no. So close. Give you those there. And give you those right. 1, 2, 3. There. I got one left here. Here you go. There you go. Oh, there's another one right there. There you go. All right. Good, good. All right. We'll just get started in just a second here, folks. We're ready to roll. Yeah. I think there's a microphone right up front there if you want it.
Can you hear me? You can hear me, yes. Excuse me. It's my special pleasure and honor to make introduction today to this very unusual and special person, Mel Slugbate, and tell you a little about him. Mel Slugbate was born to a family of career televangelists in Lubbock, Texas. Very early on, he realized his calling was real estate, and so he moved to the greatest chunk of real estate on the planet, California. He received a degree in unnecessary shopping mall development from the Big Sur Transcending Reality Correspondence School, and then went on to practice real estate in all 50 states, having held licenses to do so in several of them. Recognized as a leader in his field by a variety of organizations, all of which he founded, I am pleased to present to you the man who is to real estate what Arnold Schwarzenegger is to acting, what Michael Milliken was to the junk bond, what Ross Perot is to presidential politics. Ladies and gentlemen, I give you Mel Slugbate.
Oh, thank you very much. Oh, what a wonderful introduction. I'm touched. That was just beautiful. Thank you very much. That was just beautiful. Ladies and gentlemen, what a pleasure it is to be here before you today at the Mathematical Sciences Research Institute. This is really an honor. And I know a lot of you are sitting there and you're thinking now, how come Mel Slugbate's standing up there, okay? I mean, after all, the truth is I'm just a lowly real estate agent. And of course, most of the speakers that come here, they're famous mathematicians and mathematical expositors from all over the world. And here I am, just a lowly real estate agent. But in fact, I think what you're going to see is that the reason I was invited is because the organizers are just as excited about the financial opportunities that I'm going to present as you're going to be. Now, I have sold real estate in the swamps of Florida. I have sold real estate in the deserts of Nevada, actually on the old nuclear testing sites. I have sold real estate in the frozen tundra of northern Alaska. But in all my years of selling, I have never seen a deal like what I'm going to present to you here today. Now, I want to start off right now with a little demonstration just to give you an idea of what's coming. So if I could, what I'm going to do, I'm just going to reach into my pocket here and pull out a little money out of my wallet. And, this is a little embarrassing. I seem to have forgotten to bring any cash with me. Could I borrow a $20 bill from you just for a second here? I really appreciate it. It's very nice of you. Oh, well, I'm just hoping. You don't have, well, could I please, if you have anything like that, you know, just like $20 bill would be perfect. That'd be ideal. Thank you very much. Oh, one's not quite enough. If it's, no, one, I'm sorry, that won't do the trick. You have anything bigger than that? You have a 20 or something in there? You got a couple of ones? Don't, you can trust me. Yeah, you can trust me. Yeah, I promise I'll give you a written receipt. Do you have a 20 in there? Well, I really could I get a 20 from? Thank you very much. See, here's a gentleman on my hand here. Oh, thank you very much. I knew that would work. Okay, thank you very much. Ladies and gentlemen, a $20 bill. This is a nice fresh one. I really appreciate that. This is a nice fresh $20. Can you smell that? Doesn't that smell nice? Something about the smell of money, you know, green stuff, the lettuce, this is the good stuff. People live for this kind of thing. This is a beautiful $20 bill right here, ladies and gentlemen. I want to tell you folks, before I am done here today, someone in this room is going to be $20 richer. That's right. Okay. Now, how many times has it happened to you that you woken up and you said, I don't think I can face another day of Euclidean geometry. You know, the same old straight lines, the same old triangles, it's driving me nuts. Well, I think you're going to be very excited about what I'm going to present to you right now, because I'm going to present to you an alternative, and that alternative is called hyperbolic space. Let me just show you what that looks like right now. I'm going to show you a particular model of hyperbolic space, and this particular model right here is called the upper half plane model of hyperbolic space, and here it is. This is high-tech I'm using right here. Is that showing up okay? Yeah. This is high-tech here. This is actually not an overhead projector. This is actually a television camera. You can do this. You can go, hi, Mom, how are you? How are you doing there? See that? All right, now, this is the upper half-plane model of hyperbolic space. Let me describe to you the way this works. This is the XY plane we're looking at right here, and I'm taking for my points in this space the XY points with Y coordinate greater than 0. That says Y coordinate greater than 0. So that means I'm taking all the points above the X-axis. So right here you see the points above the X-axis right there. and that's that little stipple part at the top there, and I'm not including the x-axis. I don't want anybody calling me up later and saying, Mel, where's my x-axis? X-axis not included. And I'm going to define what I call my geodesics in this space. And a geodesic acts just like a line acts in regular old Euclidean geometry, okay? Namely, it's going to have the property that for any 2 points that are in my geodesic, the shortest path from the one point to the other also lies in that geodesic. So now in this space, I'm going to define my geodesics to be vertical half lines like that one you see right there, and also semicircles perpendicular to the boundary like that one right there. And it's supposed to have the property that between any 2 points on it, the shortest path between those 2 points is in that geodesic. Now I know what you're thinking. Mel's finally gone around the loony bin. Because it's certainly not true in this picture that the shortest path from A to B is on that semicircle, right? But what I want you to do is I want you to think of this space as if it has the property that it's completely filled with chocolate pudding, okay? And that chocolate pudding, as you go down towards the x-axis, gets thicker and thicker and thicker, okay? So what that means is if you're at this point A right here and you want to go to this point B right here, instead of going straight across, which means wading through a whole lot of thick chocolate pudding, if you go up a little bit and then come back down, it's a little bit easier to get there. And that's why the shortest path from A to B is along that semicircle right here. Okay, that's the idea. Now this particular model that we have right here is available today and today only for $299. And then you can name it after yourself if you want. It could be the Osserman model, or you could name it after your dog. You give me the $299, name it whatever you want. Okay, very special deal. Included in this model today only, we have a very nice special, which is unlimited parallel lines. That's right. I know this is hard to believe. Let me explain to you what I mean by that. When you're in Euclidean space, sitting right here in Euclidean space, if you take a line, which is that green line you see in the picture right there, and if you take a point, which is that red point that's off the green line right there, then in fact there is a unique line that passes through that point that's parallel to the green line, right? There's a unique line there, and when I say parallel here, all I mean is that the two lines don't intersect. That's what you mean when you say they're parallel, okay? So there's a unique line passing through that point that's parallel to L. That's true in Euclidean space. Take a look at what happens in hyperbolic space. You're not going to believe this. Hold on to your eyeballs. Look at this, folks. In hyperbolic space, if you take a line, in this case the geodesic, I'll take this green geodesic, I'll pick one of those vertical ones, that's an option for a geodesic, and if I take a point, this red point right here that's off the geodesic, well then in fact, there's all these other geodesics that pass through that point that miss that line. Look at them all. There's this one, another vertical line, there's a semicircular one, another semicircular one. You can imagine, there's infinitely many of them there, you can imagine all the possibilities. Infinitely many parallel lines, unlimited parallel lines in this model. Now, I'm sure a lot of you have been convinced by what I've said already that this is the model for you. But, of course, some people, they hang on to their wallet like it's just another appendage to their body. It's real hard to pry it loose, and it's not attached at the shoulder either. In that particular, so I want to show you another particular model. Maybe it'll convince you if you're not convinced yet by this last one. And this next model is called the Poincaré model, a hyperbolic space, named after that very famous French real estate agent, Henri Poincaré. And here it is. Take the unit disk in the plane here. So this is the unit disk right here. And I'm going to take all the points that are inside that unit disk. Okay? And then I'm going to take for my geodesics, diameters of that circle that go right through the origin right there, and also pieces of circles that are perpendicular to the boundary. And again, when I say geodesic, that just means for any 2 points on one of these, if I take 2 points like that right there, the shortest path between them is in that geodesic. So that's the Poincaré model of hyperbolic space. Now this particular model is available in some beautiful designer patterns due to our interior decorator, M.C. Escher. And here's the beauty right here. Okay, that's called Angels and Devils. You know, I have this on a bath mat in my bathroom in pink and purple plush. Every time I get out of the shower, it's like having a little morality tale. It's really beautiful. Now you'll notice in this particular picture right here that the angels or the devils line up along geodesics. These geodesics passing out toward the boundary. Another property you see here, which is a property of hyperbolic space, is as you get closer and closer to the boundary, to our eye, looking from outside the model, it looks like the angels and devils are getting tinier and tinier and tinier. In fact, inside the model, if you're actually in the space, they don't change size at all, okay? They don't know the difference. If they're inside there, they don't know they're any smaller than anybody else. It's just because the model we're looking at that it looks like they're far away. The other thing is, this boundary here is actually infinitely far away. So if one of these little bats wanted to get out, one of these little bats wanted to get out to the boundary, it'd be flapping its little wings from the outside view. They'd just be getting tinier and tinier. Those little wings get so small they never get there. All right. Now, how many times has it happened to you that that special someone in your life, whoever it is that's important to you, your spouse or your loved one, whoever it is, says to you, 180 degrees. And you kind of look blankly back at them and you say, honey, I don't know what the heck you're talking about. And they say, 180 degrees. This actually happened to me with my wife. Well, my ex-wife, she left me for a guy from Century 21. But she said, 180 degrees. Well, if this happens to you, I got my slide here, 180 degrees, I'm going nuts. 180 degrees. Every single triangle, the sum of the angles is 180 degrees. I don't think I can stand it any longer. Well, if this happens to you, you should say to your loved one what I said to my wife, my ex-wife. I said, honey, has Mel got a deal for you? Because in hyperbolic space, the sum of the angles of a triangle do not add up to 180 degrees. And I'm going to demonstrate that for you right now. So here, what I'm going to do first of all is I'm going to make a triangle in hyperbolic space. And I'm going to use the Poincaré model. Here's my triangle. And what I did is I took 3 geodesics. So those are pieces of circles that are perpendicular to the boundary. And at the center, they're forming what I would consider to be a hyperbolic triangle right at the center there. Okay? And you'll notice that those edges of that triangle are kind of bowed when we look at it from our Euclidean eye. It looks kind of bowed, but if you're in hyperbolic space, that wouldn't look bowed at all. Now, I'm going to measure the angles on that particular triangle. The way I measure the angles when I have bowed edges like that is I just take the tangent lines to those bowed edges, and then I measure the angle between the tangent lines. So that's what I mean when I measure the angles of a hyperbolic triangle like this. So let's take a look at this hyperbolic triangle again. Here it is. And now what I'm going to do is I'm going to superimpose over that a Euclidean triangle. So let's take a look here. Here's a Euclidean triangle that has the same vertices, but now it's got regular old Euclidean edges. And you'll notice, let me move this up just a tad, that Euclidean triangle is going to have bigger angles than the bowed edge triangle, right? The angles are going to be bigger, and therefore when I sum up the angles of the Euclidean triangle, which we know add up to 180, that means that the inner triangle, the hyperbolic triangle, must have sum of angles strictly less than 180 degrees. Pretty crazy. But of course, the first question you're going to ask is, how much less, right? So let's take a look here. Turns out that you can make a hyperbolic triangle with any angles you want, sum of the angles, anything you want, between 0 and 180 degrees. And here's how I can do it. I'm going to start with that outer triangle on that picture right there, and you'll notice it's got those geodesic edges, but actually its vertices are on the boundary of the disk, right? And we said the boundary of the disk is not contained in hyperbolic space. That's not actually part of the space. So a triangle like this I call an ideal hyperbolic triangle. Okay, it's not a regular triangle, it's an ideal hyperbolic triangle. And its angles turn out to be exact 0 degrees because the tangent line to this edge here is the same as the tangent line of this edge here. So the sum of its angles is 0 degrees. Now I'm going to take that triangle and I'm going to take its 3 geodesic edges and I'm going to start sliding them in toward the center. Okay, and as I slide them in toward the center, I'll get the whole set of triangles going in here, and you'll notice the edges as they go in toward the center, as they get closer and closer to 3 diameters, those edges are getting straighter and straighter and straighter, okay? So their angles aren't as bowed as they used to be, and it's getting closer and closer to a Euclidean triangle. And when I get in really close to that tiny, tiny little triangle in the center, those angles are almost exactly summing to 180 degrees, okay? So in fact, I can get the sum of the angles to be anything between 0 and 180 degrees there. Pretty amazing. Now, I've been doing a lot of talking here. I'm beginning to feel a little guilty about that. It's about time I let you say something here. So we're going to do a little audience participation right now, and this is kind of like a psychological experiment, kind of like a Rorschach test. Here you go. That's hard to say. Here you go. What I have here is a whole bunch of regular polygons, right? Here's a bunch of regular polygons, triangle and the square and the pentagon and hexagon. I want everybody here to pick out their favorite. Everyone's got a favorite regular polygon. You just pick out your favorite there. So you decide which one's your favorite. I only go up here to the dodecagon at the bottom there. But here's a bunch of them. All right. How many people picked the triangle? The triangle. Who's got a favorite? There's one over here, the triangle. The triangle, there's two there, two people, two brave souls, you know. The triangle, you know, I never believed that business, like psychologists say about, you know, the triangle being the simplest and it's for simpletons. I don't believe that for a second, okay? I don't believe that. I think, you know, you're brave to say that. Now, how about the square here, the regular, everyone's nervous now. How about the quadrilateral, the regular quadrilateral? Who here picks that one? Who likes the quadrilateral? Somebody must like it. There's one way in the back there, way in the back. And could you tell me, what is it about the regular quadrilateral, the square, that you like so much? What do you like about that thing? The way it looks like a square. Well, there's a reason for you. I like that. That's good. That's because you wouldn't like any of the others for that reason, would you? Okay, yeah, right? And the thing is, it's so nice. I mean, do you like the fact it's got those nice right angles? It's got right angles there, right? Nice right angles. That's so nice, right? That's such a great property of it. Well, amazing fact here. All the rest of you are holding out for the rest of them. We're actually not going to get to those, but I'm going to show you, for all the rest of you who are waiting for yours here, that we can build any one of those other ones here with all right angles in hyperbolic space. So it'll be just as nice as the square is in Euclidean space. Is that amazing? And I'm going to do an example here with the octagon. I'm going to build an octagon in hyperbolic space with all right angles. All right, let's see how I do that. So how I'm going to do that here is I want you to look at this picture here. I'm using the Poincaré model again. And first I want you to look at the outer yellow octagon right there. And that outer octagon, it's made with geodesic edges. It's got all 0-degree angles, and its vertices are all on the boundary of hyperbolic space. So in fact, it's what I call an ideal octagon with all 0-degree angles. All right? Now I'm going to take that outer one, and I'm going to start sliding all at the same time, all of its geodesic edges in toward the center. Okay, I'll get a whole bunch of octagons as I go in toward the center. And when I go in farther and farther and farther, ignore this middle one, I go in toward the center. When I get in close to the center, these edges that used to look really bowed are going to look almost exactly straight, right? And so it's going to get really close to a Euclidean octagon. Now, a Euclidean octagon has angles of 135 degrees. So that means when I started out here on the outer boundary, I had 0 degrees for my angle. When I got into the center, I had 135 degrees for the angle. Somewhere in between, it had to be 90 degrees for the angle, right? So that means there has to be a hyperbolic octagon with all right angles. Now, I'm sure a lot of you realize the implications of this statement. This means that in hyperbolic space, we can have a floor plan for a condominium octagonal with all right angles. There it is. It's called the Lobachevsky. Isn't that a beauty? Look at that there. And there you see it with the living room and the bedroom and the kitchen. And the beauty of this place is, you could never do this in Euclidean space, it's octagonal, but if you have a bureau and it's got a right angle on it, you can put it in the corner and it fits just perfect, right? It's built to fit. And that's something, $988 per month for the rest of your life. Now, I'm sure a lot of you are wondering, how can Mel possibly make these kind of offers, right? I mean, it's just unbelievable. These prices are so cheap, the deal seems so good. How can I possibly offer something like this? Well, in fact, the reason is that I can make such great offers in hyperbolic space is land is incredibly cheap in hyperbolic space. Now, why is that? Because there's so dang much of it. And I'm going to demonstrate that for you right now. I'm going to show you that there's more land in hyperbolic space than there is in Euclidean space. I'll demonstrate that for you right now. So first of all, let's just think about Euclidean space for just a second here. If I'm in the Euclidean plane and I take a disk of radius r, as everybody knows, the area of that disk is pi r squared. Okay? So the area just depends on the radius as a square. Area is pi r squared. What I'd like to do now is a little calculation to figure out what the area of a hyperbolic disk of hyperbolic radius r, what that area is, how it depends on that particular radius r. So I'm going to do that right now. So I'll do a little bit of calculation right here, a little bit of computation, and then we'll recap it all and it all makes sense and really look interesting. So you know what I'm going to do? I'm going to turn this on here and put this up here so we can sort of keep a little comparison. That'll help me when I go through this. All right. So now I want to look at the hyperbolic plane, and I want to know, in the hyperbolic plane, what's the area of a disk with what I'll call hyperbolic radius r sub h. And that little sub h will just remind me that I'm using a hyperbolic distance rather than a regular Euclidean one. Is it going to be the same kind of formula, pi times r sub h squared? No. Okay? So let's figure out what it is. Now, in order to actually figure this out, I have to tell you how to actually measure distance in hyperbolic space, right? I haven't told you that yet. So we'll use the Poincaré disk model, and I'll explain it to you right now. The way you measure distance in hyperbolic space, if I have 2 points, in this case P0 and P1, and I want to measure the distance between them, I'll call their hyperbolic distance d sub h of P0, P1. I want to measure that distance. This is going to be an integral, okay? And what I'm going to do is I'm going to integrate along the path that's in the geodesic between them. So in this case, between P0 and P1, I've got this path gamma right there, and I'm going to integrate along that path. So I'm going to integrate 2 times Euclidean path length divided by 1 minus r squared, where r is the distance from the origin to the particular point on the path I'm at that point, okay? Now it sounds a little bit messy, but we're going to do a little demonstration that'll make this really clear. We'll in fact try to measure distance, but purposely pick the distance to be along the x-axis, so it'll be really easy to see. All right, so let's do that. I'll put this back up here so we can keep track of what we're doing. So we're using that distance formula. And what I'm going to do is I'm going to take the distance from the origin to the point that I've labeled r sub e that's on the x-axis there. And r sub e, because it's just regular, that's got Euclidean coordinates. I've got the sub e meaning Euclidean coordinates. It's just going to be some number between 0 and 1. Okay, so it could be like 1/2 or 1/3 or 2/3, but it's just some number because it's somewhere between 0 and 1. And now I want to figure out, if I'm measuring things hyperbolically, how long that distance is in hyperbolic sense from 0 to r sub e. So that r sub h is what I'm trying to figure out. In order to do that, I just plug into the formula right here. And the nice thing is, because I'm on the x-axis, with this thing here that was dx, this Euclidean path length is now just dx. And the distance as I move along the x-axis from the origin to the point I'm at, which I called r on that previous slide, is now just x. So my whole integral just becomes this one right here. Okay? So there's my integral that I'm trying to do right there. 2 dx over 1 minus x squared. Now that's not such a bad integral. In fact, I can use the method of partial fractions to split that up into 2 separate fractions, just like that. Now, you know, when I was a little boy, my mama, she took me up on her knee. She said to me, she said, Mel, someday partial fractions is going to make you a rich man. That's right. You know, you can help make her dream come true today. So I split this up into these 2 pieces here, 1 over 1 minus x plus 1 over 1 plus x, and now I'm going to integrate each of those, and each of those integrates real easily into a natural log. So I get minus the natural log of 1 minus x plus the natural log of 1 plus x, and because of the properties of natural logs, I can put those both together, and I just get the natural log of 1 plus x over 1 minus x, and then I just evaluate that at limit, going from r sub e down to 0, and I get my formula right there, the natural log of 1 plus r sub e over 1 minus r sub e. And so I'll just write that at the bottom there. R sub h equals the natural log of 1 plus r sub e over 1 minus r sub e. That means the hyperbolic length of that little line segment right there is simply given by the natural log of 1 plus the Euclidean length, whatever that is, over 1 minus the Euclidean length. Now, I'm going to take that whole formula and invert it. Look at it backwards, you know. My wife said that I look things backwards right about the time she left. So now I've got r sub e. If I invert that formula, r sub e equals e to the r sub h minus 1 over e to the r sub h plus 1. Okay? So we did a bunch of calculation there. Now we know the relationship between the Euclidean and hyperbolic lengths. And I'm going to put that up here just to remember it. Because remember, what we're after is, in fact, the hyperbolic area of a hyperbolic disk. So now let's do that. I'm taking a disk, and for convenience, I'm going to pick my disk to be centered at the origin in the Poincaré disk model, and I want to know what's the hyperbolic area of a disk of hyperbolic radius r sub h, and just for bookkeeping purposes, I'll call its Euclidean radius r sub e. And now I want to find area, and to get area, I'll use polar coordinates, and I'll integrate as I travel around that disk as the angle goes from 0 to 2 pi, and as the radius goes from 0 to the Euclidean radius r sub e. And now I'll take my old integrand and I'll square it. So I had 2 over 1 minus r squared before. I'm going to square it now, and then I'll get r dr d theta for my little area, differential of area. Okay, now this particular integral happens to be a really easy one to do. You can just do a basic substitution, and if you do that substitution, you can evaluate it and you get that answer right there on the side. Okay, so I get to that point, I evaluate that at the limits, and I get this, and then what I'm going to do is I'm going to take this formula right here and plug it in for r sub e in that particular formula right there, and that gives me the next formula right here. Okay? So I'm trying to get the hyperbolic area of this disk in terms of the hyperbolic radius. I get this formula right here. Looks like a mess, but in fact it's not too bad. I can clean it up, and look at this pretty formula I get right there, which happens to be a very famous formula indeed, because that is what's called the hyperbolic sine squared right there. You believe that? Hyperbolic space, hyperbolic sine. Someone should do an investigative report of that. Look at that there. The area of a disk of hyperbolic radius h is 4 pi times the hyperbolic sine squared of the hyperbolic radius over 2. Now that's kind of interesting that you have the word hyperbolic appearing twice, but that's not what I'm really interested in. What I'm much more interested in is the fact that this thing's going up like pi times e to the r sub h, right? This term's minor. That's just a tiny term right there. This term, for r sub h getting big, is going to be the one that's important, right? This one's going to get really small. This one gets really big. So if I just look at this term, I get something that's going up like pi times e to the r sub h. All right, we went through a whole bunch of calculation, but there was a purpose. Let's recap where we are at this point, having gone all that trouble. Namely, here's the recap. For a Euclidean disk, of radius r, the area goes up like r squared. For a hyperbolic disk of radius r, the area goes up like e to the r. That's what we call exponential growth. Exponential growth, folks. So let me make this even clearer by doing a little demonstration here. Think about the city of Berkeley. All right? The city of Berkeley, when it was founded by its forefathers and foremothers, the 8 of them, they founded the city, and they said, we're going to make this city a disk of radius 10 miles, right? And everybody was happy, and that worked, and people moved in, and pretty soon people were moving in from all over, and before you know it, it was getting a little crowded. They said, look, we ought to expand the city. Why don't we expand this city by a mile? Okay, we'll expand the radius by a mile. They decide we're going to increase the radius of the disk by 1. Now, what impact is that going to have on the area of the city? We'll take a look at this. What's the percent increase in the area of the disk? Well, the disk was an area of 100 pi, and now it's going to go up to an area of 121 pi. That's exactly a 21% increase in the area of the disk. Okay, so the city increases by 21%. Not bad, right? But unfortunately, if the forefathers and foremothers of Berkeley had had the foresight to actually found Berkeley in hyperbolic space, take a look at what would have happened. If they started with a city that was a disk of radius 10, and they increased that radius by just 1, the percent increase in the area of the disk, 172% increase in the area of the disk of the city. What that means is there's more area in this outer rim in the new part of the city than the whole rest of the city combined. Okay? That's what I mean when I say that land's cheap in hyperbolic space, because there's so dang much of it. You just make your disk a little bit bigger and you get all this extra property just like that. So land is really cheap in hyperbolic space. All right. Now some of you may have noticed that in that last little discussion I made there, I talked about the units in Euclidean space. I said, 10 miles, 11 miles. But I happened to just let that slide when I was talking about hyperbolic space. I didn't actually mention the units. And in fact, I'm going to do a little demonstration here to make it clear why I didn't happen to mention the units. I'm going to hand out some rulers here. Now, this is something that real estate agents do. They hand out rulers to people with the name of their real estate agent on it, and then they jack up the price of the next house they sell to pay for it. I'm going to need these back when I'm done. Here, let me give you one of those. Here you go. There you go. Now, I'm doing these people a favor, right? Because I'm giving them a nice ruler here, and in Euclidean space, it's really handy to have a ruler. I got my own ruler right here, right? Because you can measure stuff, and it's useful to be able to figure out how long things are, and you can say, oh, that's 3.2 inches. So I did these people a favor. Okay, everyone I just gave me those rulers to, if you could just hold it up in the air for me, please. Hold it up high. Hold it real high. Now throw it down to the ground, because you're never going to need another ruler as long as you live. That's right. I'm going to demonstrate in hyperbolic space, you don't need a ruler, because hyperbolic space comes with its own units. Comes with its own units. And I'm going to show you what I mean by that. So here's how it works. I'm going to move to the upper half-plane model of hyperbolic space, and I'm going to tell you how to measure distance in the upper half-plane model. And when I tell you first, it's sort of complicated, but when I actually do it, it'll be easy. So here's the upper half-plane model, and I'll say that the distance from the point A to the point B will be, I'll just take the geodesic that goes from A to B, so that certain path I know that's supposed to be the shortest path in hyperbolic space, and I'll say the hyperbolic distance from A to B, so the distance from here to here, will be the integral along the path of Euclidean path length, ds, divided by y. Now, y is just the distance down to the x-axis. So as I move along this path, I divide by this distance, and this distance, and this distance, and this distance, and this distance. Okay, whatever that height above the x-axis is, that's what I divide by. All right, now we're going to do a real simple calculation again because it's always easiest to do simple ones. So what I'm going to do is I'm going to measure the length of that blue segment right there. Okay? So you see that little blue segment right there? I'm going to measure the distance along that line segment. Now it's a little bit funny because that particular line segment right there, that blue line segment, is not a geodesic in hyperbolic space. Okay? It would be in Euclidean space, but it's not in hyperbolic space. And what is that segment there? What I've done is I've drawn a big circle right here called a horocircle in hyperbolic space. That's what this is called here. And it's kind of a funny object in hyperbolic space because it's touching the boundary of hyperbolic space, and the boundary of hyperbolic space is infinitely far away. It's actually an infinite object in hyperbolic space. Okay? But I drew one of these here, and then I drew another circle, a horocircle right next to it, which has the same Euclidean radius. In fact, their hyperbolic radius is infinite, but that's okay, ignore that. It's just the regular Euclidean radius. And then I just took this line segment that goes from the top over to the other top, and that's what I'm trying to measure. Okay? So I want to measure that thing right there, and I'm going to use this formula right here. According to the formula, I just want to integrate as I go along that path. Now, since that path is in the x direction, my path length just becomes dx, and my formula looks something like this. So the hyperbolic length of this segment L is the integral as I go along that path of Euclidean path length over y, which is the integral. Now I'm assuming that my radius of my horocircle, Euclidean radius, is a. So both those circles are radius a, which means the Euclidean length of that line segment is L. And if I think of this point as 0, I'm going from 0 to 2a, going from here to there. Okay, so I'm going from 0 to 2a, and then I'm taking Euclidean path length, and now I'm supposed to divide by y. But you'll notice the y distance here, the distance from here to here, this distance down is always 2a for every point on that line segment right there. So that means that I'm going to be integrating, and I'm always dividing by 2a. Now that integral, that's one I can do. That's just 2a over 2a equal to 1. No units, right? I didn't tell you any units, right? It's just 1. There it is, 1 unit long. So that thing's 1 unit long. You'll notice if I take my length a there to be really short, so I get 2 shorter circles, that distance also would be 1 unit long, just 1 unit long. That one, the tiny little one down there, you can't read it. That's 1 unit long. Now, just for convenience, because there isn't a name for these units, we now call these slugbaits. So that's 1 slugbait long. Okay? So there's 1 slugbait right there, and that's the units in hyperbolic space. Now, what's going on? You have to wonder, well, how come this works this way? Well, the reason is because in Euclidean space, you can scale things up and down, right? Euclidean space, you can make an octagon, a regular octagon, which is really small or really big. You can make them big, you can make them small. You can scale things up and down. In hyperbolic space, the scale is fixed. Once I decide, for instance, to make one with all right angles, that completely determines the edge length on my particular octagon. In this case, it's about 1.528 slugbaits. Edge length right there. So you can't scale things up and down in hyperbolic space like you can in Euclidean space. All right. I've been saying a whole bunch of stuff here, but I'm sure a lot of you are wondering, when's it going to get to the 3-dimensional stuff? We can't live in 2-dimensional hyperbolic space. Let's see some 3-dimensional action here. So what I'm going to do now is give you a couple of models of hyperbolic space and a couple of nice developments we've been working on in hyperbolic space I think you're going to find very exciting. So here's the first. It's a really nice model, a really nice development. Oh, geez, that's not the right picture. Sorry about that, folks. That's not our development. Here's our development right here. Slugbate estates in hyperbolic space. Isn't that a beauty? Now the idea here is this is just like the upper half plane model of hyperbolic space, only this is now the upper half space model of hyperbolic space. So I'm taking all the points in x, y, z space with z coordinate greater than 0. So everything above the xy plane. I've got these nice houses which are sitting on these hemispheres perpendicular to the boundary. Now those hemispheres are in fact what I would call geodesic planes in hyperbolic space. Okay, so I've got those hemispheres sitting there. Then there's a nice little field of geodesics sitting over here. I also have a vertical half plane, and that also is a geodesic plane in hyperbolic space. The amazing thing about these geodesic planes is that they inherit from hyperbolic space a 2-dimensional hyperbolic geometry. So that means your house is sitting there and your front lawn has 2-dimensional hyperbolic geometry while you're living in 3-dimensional hyperbolic space. It's really quite a special experience. Very, very nice. Those are available at $129,995 and up. Really some beautiful mansions in there. The other nice thing about hyperbolic space is it's a really great place to play croquet. Look at that. You know, you got your horror balls, you got your little geodesics there, so that's another advantage. But some of you may have been holding out so far when I'm talking about these various things I have here, some of you may be holding out for something really special. I think you're going to really like this next thing we got going here. This is perhaps the crown jewel of all of the various developments we have going at Slugbate and Mossbutter Real Estate Agency. Here it is, folks, the Slugbatheon. This is a beautiful building right here. Here it is. This is the Slugbatheon. Now, this particular building right here used to be in Venice, Italy. And we went over there, and we took it apart brick by brick and stone by stone and moved it over here to Hyperbolic space and put it back together again. And then we broke it up into 35 luxury condominiums. You can move into one of these babies. This thing is sitting right on top of what we call a horror ball. Okay, so that's the three-dimensional analog of a horror circle. This is a horror ball, this whole big ball, and it's sitting down touching the boundary plane there. So again, this is an infinite object. The amazing thing about the boundary of that horror ball, called a horror sphere, is it inherits a Euclidean geometry from hyperbolic space. So it has two-dimensional Euclidean geometry. So here your front lawn has two-dimensional Euclidean geometry while you're living in three-dimensional hyperbolic space. You don't get so nauseous. You know, it's a little easier to deal with. Sitting next to this thing is another really interesting object, which is the three-dimensional analog of an ideal triangle, and that's called an ideal tetrahedron. Okay? And that's a tetrahedron in the sense that it has four faces, and each of its faces is lying in a geodesic plane. So you see here there's a vertical plane right here that makes up part of this face. This face is sitting in a vertical plane there. There's another vertical plane there, another vertical plane in the back. Those are all geodesic planes in hyperbolic space. And then the bottom face is on a hemisphere. Okay? And any two of these faces intersect in a geodesic, either one of these semicircular geodesics or one of these vertical geodesics. This thing actually has four vertices, and this is the part that's a little hard to see. You can see that vertex there, and that vertex there, which are actually sitting on the boundary hyperbolic space there. But it doesn't look like there's another vertex at the top. But in fact, those three vertical lines are actually getting closer and closer to each other, because remember, the way to measure distance in hyperbolic space is you divide by the distance from the boundary plane, and as we go up, you're divided by a bigger and bigger number. Those things are getting closer and closer together. So in fact, those three lines are converging at a point, which is the fourth vertex in this ideal tetrahedron. Okay. Well, now I realize some of these deals I've been talking about are a little pricey, right? I mean, not everybody can afford this stuff. So what I want to do is introduce one more model that I have here that's a little more in some people's price range. But first, let me just mention one fact which to help to understand what I'm going to do. One way to visualize what's called a torus, which is just the surface of a donut, is to think of it as taking a square. You see that square I have at the top there? Taking a square and gluing the edges together. So if I take that square and I glue the top edge to the bottom edge, I'll get a cylinder. I'll just take my square and I'll glue it together and I'll get a cylinder. Okay? Then if I take the side edge on the left, which is blue, and glue it to the side edge on the right by pulling them around and gluing those together, I get what's called a torus, the surface of a donut. Okay? So I can think of a donut or a surface of a donut like this, or if I want, I can just think of it as that square at the top, where I keep in mind that if I go off this edge here, I come over here, and I go off this edge here, I come in down here. Okay? All right, well, that's just preface for one of the really nice items we have right here. This is a little less pricey. This is a wonderful little efficiency we have right there, made from two ideal tetrahedron hyperbolic space. Okay, so what we're looking at here is we're looking at one ideal tetrahedron on the left and another one glued together with it on the right. So you got those two ideal tetrahedra there. And then what I'm going to do, just like we did with that square to make a torus, I'm going to glue the back face, which is labeled A, one of that vertical face back there, to the front face, which is labeled A prime. I'm going to glue that face labeled B to the bottom face B prime, and that face labeled C to the back face C prime. So I'm going to take this thing and I'm going to glue it up like that. Now I can't actually do that for you because you can't really see that in three-dimensional space. But that's what I'm going to do. And the beauty of this thing, you got these two rooms right here. If you're sitting in this chair right here, what happens is if I look out in this direction, I'm looking straight towards the face C prime. The face C prime to the face C. I'm looking right here. I can see my own butt. Isn't that something? I can look and see my own butt in this space. It's really something special right there. And it turns out that the volume in each one of these tetrahedra, you can actually calculate the volume in each one of these tetrahedra, and each of those tetrahedra has a volume 1.014 cubic slugbates. So the total volume of this space that you're living in is 2.02988 cubic slugbates. Okay, so you can actually calculate that. Now, of course, you're probably wondering, well, if I did live in there, exactly what would I be living in? You know, I mean, what is this object? And this is where stuff gets weird. I realize so far it's been a little weird, but this is where it gets really weird. Okay? This thing, if I take those tetrahedra and glue them up in that way, actually corresponds to a knot. Okay? So this is a knot right here called the figure 8 knot. Okay, that's a particular knot in space. You can think of taking a string, tying a knot in it, and gluing the two ends together. Now, that place where we be living, that efficiency, actually corresponds to, this is where it gets really weird, space minus that knot. Now, the best way to think about that is just think as if space was completely filled with green jello. Okay? So the whole room's filled with green jello. And then a little worm came along, and it chewed out where that knot was. So it drilled a hole right through the space and followed the path of that knot and drilled it out. So now I have space minus a knot. Okay? Now, of course, you're sort of wondering, well, space minus a knot, does that mean if I lived there, that if I put my arm where the worm had drilled out the space, there'd be a hole in my arm where my arm was, right? That sounds like, what does it mean to talk about living in space minus a knot? In fact, it doesn't mean that at all. The idea is that, in fact, it's more like this. This is my dog, Ralph. And so Ralph here, as he moves towards the knot in this space, he's going to look from our eyes outside in this model like he's getting smaller and smaller. He'll never actually get there. It's infinitely far away. His little paws, he's going in that direction, his little paws, tinier and tinier. He never actually gets there. Incidentally, he is for sale, by the way. And so that's why, in fact, the knot is infinitely far away in the same sense that in that particular model here, if I headed out in this direction, I'd never actually get there because that's infinitely far away right there. Okay, well now, of course, maybe you're not interested in that particular one. In fact, it turns out that for any old knot I want, take any of these knots right here, the ones that have a little blue underline thing, that's their volume. Now, I realize you can't see that very well, but right up there you see the figure 8 knot. Then you see one that has 0 volume, but then you see one that has an actual volume there, and then another one, these other ones, and the volume's a little hard to read, but we're selling these babies for $50,000 times the volume. It's really a bargain, I'm telling you, and you can live in any one of these, and these are what we call hyperbolic knots. And in fact, a lot of the theory of these things was invented by Bill Thurston, who's actually the director at the Math Sciences Research Institute. Okay, so I think I'm going to finish up right now. I kind of want to make it clear that, my goal here isn't just to make money. I certainly hope that people realize, when opportunity comes knocking, you gotta unbolt that door, you gotta undo the chain, you gotta embrace it, let it in and embrace it. But on the other hand, the important thing in life isn't making money, right? The important things in life come from inside here, right here. Okay, that's what's important. So what you really should do, it's not coming from here. This isn't where happiness is. So what I recommend everybody doing when they leave here today is just come up to this table up here and just throw your wallet down and walk away. Walk away from it and try to find happiness other ways. Okay, I'm just going to finish up with a few credits here. I'm just going to run my credits, and I want to thank you all for coming here. And let me just run the credits here. Thanks very much. Do 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 dun 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 do 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 dun 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 do 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 dun 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 do 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 dun 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 dun. Thanks, folks. Thanks very much for coming. Thank you, folks. Thank you very much.